Welcome to Suchitra's Defense. I am Jonathan Williams, professor at UH and nominally Suchitra's advisor, but all the advising was already done by the person on your left, Professor Karen Oberg at Harvard University, and she will give a little end of the introduction after my introduction. Okay, so the way this works is I will do an introduction. Suchi will talk for about 45 plus minutes. There'll be a public question session, so think hard, come up with questions. Yeah, tell me what this is. If you don't know what this is by the end of Suchi's talk, then well,
I wouldn't have done a good job.
Anyway, so we'll have this public session, and then by about an hour around noon, we'll go into closed session where the committee will meet, and the committee members are Gary Huss, in the audience here, Dan Huber, and then online Karen Oberg and Edwin Bogut, and me. And we'll have a closed session that will last for up to an hour, no more than an hour. And then there will be, if all goes well, and I assume it will, there will be celebratory drinks and food and so on down in the courtyard. So if you want to put off lunch, go ahead and dig in at 1 o'clock. All right. So let's start with a little bio. So Suchi grew up in the Bay Area and went to American High School in Fremont, which is a great name because apparently most of the kids there are probably immigrants or at least first gen. A lot of the kids there are. So I think it's a very appropriate name, school. She then moved north about 10 miles or so up to Berkeley for her bachelor's in chemical engineering and astronomy. Came to Manoa about 5 years ago. She did a 699-1 with Eric Gaidos, who's in the back there. And then 699-2 with me, got a master's degree. And then most importantly, she got a graduate research fellowship, which gave her the independence to do what was a real passion, which was astrochemistry and lab work. And she was able to secure a position in Karen's group over at Harvard Smithsonian CFA, where she's been for the last 3 years. In addition, she's achieved a number of other awards, not as famous as the GRFP, but quite lucrative and allowed her to get independence, to travel, to attend other meetings and so on and so forth. And that's something that's very valuable in these times where federal funding is getting squeezed. So kudos to you for that too. Okay, now the fun part. So cute baby photos and so on. So you can see from an early age, she was into space. She's been playing piano forever, I think classically trained since age 4. Already on the computer, clearly academic. So the markings were clearly there for a future in STEM. California, yeah, so she continued in music. She was on the engineering team building a race car at Berkeley. This is very brief. There are many, many other things. She was a lifeguard at East Bay Regional Park. Where are you? Oh, you're here. But where I first met her was with this guy, Dick Planbeck, who's in the radio astronomy lab at Berkeley. I came by, I've known Dick for a long time. I've worked with him. We've written papers together. And I passed through Berkeley. I spoke to him in 2017, and he introduced me to Suchi. And she's a very gregarious person, if you don't know. And so she kept in contact and remained very interested and kept on saying, how interested she was in coming to Hawaii. So I was very happy when she did indeed come to Hawaii. And here's a few photos, right? So the obligatory moped plus surf rack. The obligatory Mauna Kea photo, volcanoes, outreach class. This is a fun class where we built radio telescopes out of basically wood and polystyrene and aluminum foil. She was also involved in Code Astro, where she TA'd. And there's a couple of other IfA students there, Maria, and I forgot to look him up. Jessica Liu's student, anyone remember? Matt Hosek. So she did Code Astro for a couple of years. She'd written for Astrobytes. And then she got the GRFP. Oh no, hang on, there's more. There's IfA Life. So lots and lots of photos. Again, just a selection of beach trips, diving, all sorts of fun things, meetings, hanging out with the future grad chair, hanging out with the director. Then she got the GRFP and moved over into the Boston area, where again she made lots of friends, went to weddings, had parties, hung out with the Oberg group, hung out with visiting IfA students who passed through Cambridge. But most importantly, she spent innumerable hours down in the basement working in the lab on Space Kitten, which she'll tell you all about. I want to give a shout out to her parents who are here, and a very nice acknowledgement that Suchi gave, which is that they, she does astrochemistry. Her mother was interested in chemistry. Her dad was interested in space. So it's a very nice sort of circular coming together of the family interests. So I thought it was very nice. The thesis is dedicated to them. Welcome. We're glad to have you. Thank you. Okay. What are the next steps? Assuming all goes well. She's going to head over to the astrochemistry group at Max Planck, working with Paolo Caselli, who's also a longtime collaborator of mine. So I'm excited to see you join that group, work with her. I'm sure I'm going to see you there. Right in the heart of Europe, Garching about 30 minutes north of Munich. A great place to do astronomy, a great place to live. So congratulations on that. Now you might say, what is my role in all of this? Suchi and I did write a paper for the 6992, but I have absolutely nothing to do with the work she's about to show. So really, my role is this. All the credit really goes to the Oberg astrochemistry group over at Harvard. And there's a great bunch of people there, observers, theorists, modelers, lab specialists. And I like this because, academics is a tight-knit group. So I went to grad school with that guy, Dave Wilner. Sean Andrews is my first PhD student. Lexa, you'll know Clara Ross, who worked with us, helped us with Keck observing when she was an undergrad. And then the most important person here is Suchi, of course. The second most important person is Karen, who is head of the group, and I'm going to pass it on to her. So Karen, take it away.
Thank you so much. And thank you so much for letting me say a few words about Suchi's thesis work that she has been doing with us here at Harvard. I am, of course, very sad to not be there in person, but also very grateful that I can join you remotely. So I think what you will learn over the next 45 minutes or so is that sulfur is much more central to astrochemistry than maybe you would have thought coming into this thesis talk. And also that sulfur astrochemistry is very poorly understood. So if you take those things together, you might wonder why there hasn't been, in some sense, more laboratory experiments on the kind of organic sulfur chemistry that Suchi will be talking about. And the simple answer is that these experiments are dangerous and difficult, which means that it takes someone, I would say, of both physical and intellectual courage to want to pursue them, some persistence in talking a professor, that's me, into actually having them done in the lab, and a lot of ambition to want to do a thesis that's hard and that makes a real impact. Now, for those of you who know Suchi, it should come to no surprise that this is exactly what she chose to do her thesis on. So part of what Suchi sets out to do is to answer some very fundamental questions about sulfur chemistry, and especially sulfur that is incorporated into organics, how they react in icy grains. And you will get, and she has some really beautiful results on what these fundamental properties are, and have in that sense resolved several of our sort of known unknowns about sulfur organic chemistry. But what I find to be the most exciting is the unknown unknowns and the answers that have emerged to those in the thesis. There are some questions we knew to ask about sulfur chemistry coming into this, but there are several that we had no idea that we should be asking them, that Suchi has sort of revealed to us that they are actually really important. And I think, not to give too much away, but most important of those on how big of an impact sulfur molecules can have on other molecules that resides close to them. And I think actually there's a little bit, in my mind, back to the drawing board when we're thinking about the chemistry that's going on in icy interstellar grains and how important it is to think about it as a system where different kinds of molecules impact each other in surprising ways. So this has been a really cool and fun adventure to walk along with Suchi. As Jonathan said, the advisor is at best the second most important person in this journey. And this has really been a thesis that has been fueled by Suchi's ambition and creativity. And I'm just really excited to hear her share her work with all of you. And again, thank you so much.
Can everyone see this okay? Also on Zoom? Okay, so hi everyone. Thank you, Jonathan and Karin, for those lovely introductions. Today I'll be talking to you about my dissertation work entitled Organosulfur Chemistry and the Birthplaces of Planet, Comparative Study of Sulfur versus Oxygen in Interstellar. Now, that is quite a mouthful. So I thought that I would actually dissect this title into pieces to introduce each topic and how they work together. First, I want to start with the biggest scale, which is the birthplaces of planet. We have to start with the regions in between stars, called the diffuse interstellar medium, or the ISM. You can get clumping of the dust and gas in these regions, which forms cold, dense molecular clouds. And once those clumps undergo gravitational collapse, you end up forming protostars and protoplanetary disks, which are baby stars and baby planets. These eventually evolve into a stellar system. And once the star evolves and eventually dies, that material is returned back to the ISM. This cycle has to continue multiple times in order to create the chemical complexity that led to life as we know it here in our solar system. And so it behooves us to think about how we actually form these stellar systems. When we start with the cold, dense molecular cloud, you can split into 4 classes, which I'll walk through, but it's only to introduce some of the observations and what they can tell us, not any details about how we actually classify them. But you have a class 0 star, where you have a protostar deeply embedded in an envelope, and a class 1 source, where the accretion disk begins to form and you get outflows that release those excess angular momentum. And so these are called embedded sources. And like Jonathan said, we worked together on this ALMA large program headed by Nagoyoshi Ohashi. And these are ALMA observations from the Atacama Large Millimeter Array in Chile. This is the highest resolution data set yet of these embedded sources. And we're looking at them through the radio telescope. But these are all a variety of sizes. If we collapse them all into the same size, we actually see there's a diversity in their structure, in their sizes, whether they have binary. I'll just introduce my little source over here, Ophiuchus 43, and introduce some things that observations actually tell us. Radio observation let us probe the dust and gas of young dust. So if we zoom out from what image I just showed you, we actually can trace the envelope. And this we can trace with CO and its isotopic lab 13 CO. And we can see those are probing different regions. You zoom in, you get the continuum image, which is the dust, and the solid states. And you can actually probe molecular tracers within these disks. And this is kind of unique to highlight because this is a binary system that formed from the same dust and gas. But we see that SO is isolated to one part of that one star. And so this tells us that even within the same dusty disk from which a star forms, it can have very different chemistry. Note that the typical dust to gas ratio is 1 to 100. So you have 1% solids and 99% gas. Next, we evolved to class 2 system. And this is when a pre-main sequence star has reached its final mass and you form what is known as a protoplanetary disk. There have been other large programs looking at class 2 disks, which look markedly different. We see substructures, we see these gaps, we see spirals. And so this is just the dust. There was a follow-up that looked at the molecular tracers. And so these are 5 different disks and different molecular tracers. And we can see that you have difference in chemistry across different disks, and as well as in the same disk. So this tells us that chemistry is actually coupled to, intimately coupled with the stellar system that it's part of. And finally, we have our class 3 source, which is low mass disks with little to no accretion. I want to emphasize this because each region has different physical properties, and those physical properties actually affect the chemistry. And I'll just walk you through a few of the different radiation temperature densities that you might consider and why the chemistry might be different. You can have warm inner envelopes that are primarily traced by complex organic molecules. These are high temperatures, high densities, very intense radiation. You have the cold outer envelope, opposite of that, but you actually can get cosmic ray radiation. Then you have these outflows where you can have high temperatures, high velocities, so different tracers depending on whether it's a jet or an outflow. And then you have a protoplanetary disk, which has a radial temperature gradient, as well as differences in density, and radiation fields that vary both radially as well as vertically. These disks can actually interact with the cavity, the outflows, and you can form these regions called cavity walls that also have very intense radiation. So all of these show us that the chemistry is very coupled to the local environment. But all I showed you were gas tracers. Actually, in fact, people thought that gaseous reactions were what led to the chemical complexity that we observe because of the 1 to 99% ratio that I mentioned earlier. But it actually turns out those gas phase reactions are not very efficient, and you actually have to think about what's happening in the solid. And so in the midplane, which is the center of this disk, you can have these dry, dusty rocks, but in the outer part, you have these icy grain mantles. This is what I'll be focusing on today. But I thought we should do a little bit of anatomy of an icy grain. So you start with silicate carbonaceous grain. You can form icy layers, typically water. That's the most abundant matrix constituent. But you can have layered ices with other hypervolatiles like CO and CO2. And all of these can undergo, you can have many different reactions that can happen on these icy grain. And so some chemical processes that I'll be talking about throughout this talk, you can have adsorption, which is when a molecule in the gas phase gets stuck onto the grain, condenses directly from the gas to the solid. You can have desorption, where solid state molecules actually sublimate into the gas. This desorption can actually be induced by UV photon absorption. Once it's in the ice, it can actually diffuse and move through the matrix and react with other ice constituents, leading to chemical complexity. But once you have that, you can actually also absorb that photon and then dissociate it right back. And so there's a lot of processes that I didn't even mention, thermal effects, cosmic rays. But the main point is all of these can happen individually or all together. And these processes drive the chemical complexity that we need in order to form these biologically relevant large molecules that we know that the icy grains are conducive to leading to. The building blocks of life as we know it depend on hydrogen, oxygen, carbon, nitrogen, sulfur, and phosphorus. And I set these in the order of their abundance, both in the universe and in terms of life as we know it. So sulfur is the 5th most abundant out of these 6 biologically relevant ones and 10th most abundant in the universe out of 118. It's important both for astrobiology. So it's present in 2 amino acids that all of us have right now, cysteine and methionine. but it's actually even thought to be part of primordial Earth's genetic alphabet. So instead of canonical oxygen-bearing adenine, guanine, cytosine, thymine, if you remember from biology, all the nucleobases in our DNA, it was actually sulfur substituted in order to reach the origins of life as we know it. So sulfur is quite important in that way, but it's also important in terms of planetary habitability. The origins of life as we know it required the presence of a solvent, water, but also needs sulfur-bearing species and nitriles in order to kickstart these, the prebiotic chemistry. So it's important for us to know the sulfur chemistry in the birthplaces of planets and in interstellar ices. Out of the 330 total molecules detected in the ISM, there are about 40 sulfur-bearing species detected in the ISM, only 6 in disks where we think planets form. And so people thought, okay, if it's not in the disk, if it's not in the gas phase of these disks, maybe it's in ice. But there's only one that has been actually confirmed in ice with a tentative other detection. And notably, there's no H2S. And this is the most abundant in comets, which are thought to preserve the initial solar cloud from which our solar system was formed. So even with sulfur's high abundance, we can account for about 95% of the sulfur budget. And this has been called the missing sulfur problem since the 1990s. How can we understand it if it's so difficult to observe? Well, we use our periodic table. Theoretical modelers leverage the fact that oxygen and sulfur are on the same group in the periodic table. So this is where the sulfur versus oxygen comparison is made. Same group elements are isoelectronic. This means they have the same number of valence electrons. These are the outer shell electrons that are responsible for an element's reactivity. So theoretical modelers assume that we can infer how sulfur-bearing species form based on their oxygen analogs. The most updated of these models, which predicts that the missing sulfur could be locked up in organosulfurs. Organosulfurs means a sulfur compound containing a CH bond. The simplest complex of these is methylmercaptan. Thank you, Jonathan, for this visual over here. And if you see it referenced in the rest of the talk, CH3SH, MESH, or thiol. And it's important because it's analogous to methanol, which is the most abundant complex organic molecule in the ice and in our observations, and it's also the most well understood. So this is where the organosulfur chemistry comes into play. Methylmercaptan has been detected towards molecular clouds, protostars, and our comet, 67P, but notably not in disks. And so to understand whether these organosulfurs could actually be the proposed sulfur state, we have to empirically characterize its fundamental astrochemical property. This dissertation has implications for several different interdisciplinary fields. In terms of astrophysics, we want to answer, should organosulfurs be observable across planet formation timescales, and could they be the bulk sulfur reservoir? Astrochemically, and also just pure chemistry-wise, can sulfurated species affect other icy molecules? And do sulfur and oxygen actually behave analogously in the solid state? And then astrobiologically, we want to know in what form can we expect sulfur to be delivered to protoplasm. So to ground the experiments, I will keep showing this edge on disk to ground you. So in this, I will highlight the different IC processes in disk. So you'll see an edge on disk in several slides. Molecules condense out radially, and that's by virtue of this temperature gradients. And these form what are known as snow lines. So this is typically in sequential order of water snow line at around 1 AU, volatile, so CO2 at around 5 AU, that's where Jupiter is, and then hypervolatiles, or the CO snow line, way out where Uranus is. So these typically are formed sequentially based on their condensation temperature. However, in reality, ices are not a single component like this. They're actually mixture. And so you can actually have entrapment of these hypervolatiles or volatiles at the water snow line because of the water matrix. And so this has been well studied since the 1980s. And you can actually lock in a bunch of these hypervolatiles much closer in than you would previously. Once a molecule is in the ice, it's subject to processing. So UV radiation forms distinct regions in disk. You have the gas, you have the unprocessed ices, this is close to the midplane, shielded by the other dust and gas. Then you have a UV-rich upper layer in which molecules are not expected to survive because of the incident radiation is too high. But then you have this active photochemistry region. Since UV radiation can both form and destroy molecules, this active photochemistry region is something that tells us about a molecule survivability across planet formation timescale. So understanding an icy molecule requires us to understand both parts of it, the sublimation dynamics and the photochemistry. So how do we simulate these disk conditions in the laboratory? We have 4 ultra-high vacuum chambers in the Organosulfur lab at the CFA. On the left is Space Kitten. On the right is Space Tiger, which goes from our simplest to most complex. I know this can be a little bit daunting, so walk with me for a brief experimental procedure with these drawings I made. So we first have to get to low temperature, low pressure using a closed cycle helium cryostat. This gets us down to 10 Kelvin and 10 to the minus 10 torr, which are comparable to what molecular cloud conditions are like. For context, our atmosphere is 760 torr. We then have to introduce our molecules into the chamber. So you have a doser that connects to a gas line, and then it leads to this IR inactive substrate. This is, for context, we're here in the disk. We can process these ices thermally, so we can heat it and induce sublimation. And we can also process the ice via irradiation. So you have a UV lamp. There are other ways to induce this via electron or atom bombardment and even lasers. The first data product comes from the infrared spectrometer, which allows us to characterize the ice phase. This is just a sample spectra. The second data product is mass spectrometry, which characterizes the gas phase. And I'll be showing a lot of these so-called QMS curves, so I wanted to highlight what exactly you're looking at. So as you're heating up the ice, at a certain point, you're going to release all of them into the gas phase. There's only a finite amount that has been deposited, so you come back down. The integrated area here gives you the total amount of species. And this start of the curve is the ice-gas boundary. And I mentioned this earlier, that's the snow line. So that's where you actually want to characterize the snow line. So that brings me to my first chapter, determining methyl mercaptan snow line. What is methyl mercaptan in its gas or ice phase? This means we want to know what temperature does it sublimate? Does this change when it's binding to water, which is the most abundant constituent in ices? And can methyl mercaptan be entrapped when mixed with water? However, as Karin alluded, there are many more surprises from this study. I want to first highlight what kind of ice matrices we're actually making. You can have pure ices, which are probing the interaction between the same species. You have layered ices in which you have a thick water ice that's been deposited, and you have less than one layer of your target species, and you're actually probing that interaction between the molecule and the water. And then finally, you have a mixed ice, which allows us to characterize the entrapment and think about all the different binding interactions that are happening. Each of these matrices is going to have different desorption kinetics, or in other words, how they sublimate, which can be seen by these QMS curves that I alluded to. Those QMS curves have an actual name called temperature programmed desorption. We're heating up the ice and we're inducing desorption. This is just a pure methyl mercaptan layer. And we can, I don't talk about this much in this talk, but I ran computational chemistry calculations to understand what was happening in my experiment. So these are just visual representation of the interactions that we're looking at, just to guide you as to what these curves are showing. Then you have methanol, and this tells us simply that methyl mercaptan is more volatile than methanol because it desorbs at a lower temperature. But this is truly not a realistic scenario. We actually want to think about how it looks when it's layered with ice to look at the binding interaction with water. Now here I have a water to scale just to show you when water desorbs. And here we're probing this interaction over here. And what was surprising to us is that methyl mercaptan is kind of not showing any different. And I want to note that don't worry about this bump here yet. But methanol, on the other hand, is really hugging that curve. It's very different to what it looks like in its pure state. So what we can say from this is methyl mercaptan is indifferent to whether it binds to itself or with water. Methanol interacts significantly with water, and that makes sense because methanol can undergo hydrogen bonding, the OH. So qualitatively, we can say methyl mercaptan's snow line should be further out than methanol. But this is not, we actually want to know how we can actually derive this in order to input it into astrochemical model. And so this curve, the start of the curve that I said, the ice gas boundary, has been well described by this Polanyi-Weiner equation. And all we want to get from this is this attempt frequency nu and this binding energy. This EB tells us how strongly the molecule is binding to a particular surface. And this nu is actually something that tells us the attempts that it makes to escape the potential well, if you think of the ice surface as a potential well. So typically, you have a harmonic approximation where this interaction is thought of as a spring. But molecules are not point masses, and especially large ones like methyl mercaptan and methanol. Beyond the scope of this talk, but I do validate a new method that accounts for all degrees of rotational and translational freedom that allows us to get better binding energies for large molecules. And this can shift your previous values by 1,000 to 2,000 Kelvin, which can be several AU and snow lines, depending on your disk model. Here is the layered submonolayer TPD curves. So this is where you're probing that interaction. And I just wanted to highlight here that even as we're increasing the layers by tenths of layers, methyl mercaptan is still coming off solely with its pure, it's following its pure desorption curve, versus methanol is actually continuing to hug that. I want to note that this little peak doesn't increase, so we can say that that's just what has been entrapped at the surface layer of the water matrix. So we actually don't think that's really probing any binding. You'll see later on with the entrapment studies. But this is just to highlight why we know that this bump is actually not indicative of binding. Here's a summary of the binding energies from my paper. The true values don't matter. I just want to highlight that the methyl mercaptan and methanol are the same. Methyl mercaptan to itself and to water is the same. And methanol is a little bit higher, and we expect methanol water to be higher. Here is where entrapment comes into play, and I wanted to first guide you how we actually even determine entrapment. And here I just show fiducial 3-component ices. So CO2 is one of the bulk ice matrices, so we wanted to choose it as our representative 3rd component. This is when pure CO2 generally desorbs. This is when pure methanol comes off. And then here's where water recrystallizes. And this is water co-desorption. I want to highlight what this water recrystallization is because it's important. It allows for the abrupt release of entrapped molecules when water restructures, and dubbed volcanodesorption. And so you can think of when water restructures, it moves a little, and it opens up the pores enough to let the molecule escape. So here's methanol, and we can see it comes off in this matrix, and it's pure during the recrystallization and during co-desorption. And what we define as entrapment is what comes off after its pure desorption. Here you can see CO2. It comes off at its own, and it comes off at the later ones as well. Now this is where it's surprising. Methyl mercaptan is 100% entrapped, but I just showed you that it doesn't bind to water. And not only that, CO2 is majority coming off with methyl mercaptan at the volcano peak as well. This was very surprising because we had never seen 100% entrapment, total entrapment ever in experiments before. And so I ran it with a bunch of different conditions, thick ices, thin ices, different dilutions. And unless we were in super volatile rich cases, it was coming off at this volcano peak exclusively, no matter what. This has never been seen before. So what we found is that methyl mercaptan's size is actually inhibiting its ability to diffuse through the water matrix and escape, even though it really wants to. And from this, we were able to constrain the pore size of a water matrix for the first time experimentally. And that's by doing some computational calculations and getting this value over here, the largest distance of an atomic pair. We actually wanted to see how does this affect bigger molecules. So I did this with methanol as well. And what was really surprising is that not only is methanol 100% entrapped, but it essentially negates its binding to water. It's forcing all of it to come off at the volcano. And we know that this is happening because methyl mercaptan is plugging the water pore, or what we call as acting as a cork. Because in this case, you can see methanol only escape when methyl mercaptan escape because of the difference in their leading edge. So the astrophysical implications of this study, I do predict the snowline location. And so we use a fiducial disk model from this paper by Karin and Robin Wordsworth. And what we end up finding, more importantly, is that we have these binding energies, we can predict these snowline locations, but what actually might matter as to where the snowline is actually when it forms, is it with or without water? Because if methyl mercaptan forms with water, it's going to be 100% entrapped no matter what. And so something that I wanted to look at based on this was, can this extend to larger molecules? And so this is what Karin has lovingly dubbed the champagne desorption effect rather than a volcano. And so to illustrate what is happening, we have this little molecule here, and you can think of methyl mercaptan as a plug for the water pore. It wants to escape, but it can't because it can't escape this matrix. Only when the water ice restructures and methyl mercaptan is released can all of those entrapped molecules release. And because they're building up this pressure, like what happened with methanol, it wants to escape the moment that the methyl mercaptan escapes, and it comes flooding off at the volcano. But this is only because you have a molecule that's acting as a cork for this ice. So somewhat roundabout chapter that ended up happening is organic mediated ice entrapment. This was such a unique effect that I wanted to see, is this unique to methyl mercaptan, or can other large organics exhibit this as well? So the questions I wanted to answer was, can methyl mercaptan enhance entrapment of hypervolatiles? I'd only done this with CO2 and methanol. Are molecules similar to methyl mercaptan also 100% entrapped? And if so, can these actually plug the pores of a water matrix? And so the difference between methanol and methyl mercaptan is only 15%. And so this was really interesting because we have a hydrophilic substance like methanol that really loves water but is not 100% entrapped, and a hydrophobic like methyl mercaptan that doesn't want to bind to water but it is. And so we have this really cool constraint of what the pore size can be. It has to either be bigger than methanol or smaller than methyl mercaptan. And so if large organics form with water, could they be available at high abundances at the water snowline where planetesimal formation is actually very efficient? And if they are efficient plugs, then we could be severely underestimating the volatile inventory of volatiles and organics close into the inner disk, and thereby what goes into forming planets. And this could not just shift that middle snowline inward, but actually the hypervolatiles as well. And so our typical understanding of how snowlines are distributed might not actually be the full picture. And so first, I wanted to showcase that methyl mercaptan can indeed entrap hypervolatiles. So I did it with CO and methane. So this is just a binary entrapment of CO to water. And this is methane to water, and it's 15% entrapped. And the moment that methyl mercaptan comes in, we see that it's about 2 times larger. And something to note is that it ends up going to 0 over here, if you look at that. In the binary case, it can actually continuously desorb by making its way through the ice matrix. But the moment methyl mercaptan is there, whatever is close to the surface can escape. But once it reaches that pore, it can't, and it comes off at the volcano. And then for methane, it's increased by 4 times, so 65% entrapment. So then I looked for candidate quarks, and the way that I decided this was large molecules that we expect to be in ices, so the next degree of complexity more than methanol, and also ones that don't exhibit hydrogen bonding. So methyl cyanide, which is smaller than methyl mercaptan, dimethyl ether, which comes from methanol irradiation pretty easily, dimethylamine, and benzene. So this probes nitrogen bearing, sulfur bearing, oxygen bearing, and also hydrocarbon. And this is increasing in molecular size. So here I show their pure desorption curves, and I show the volcano and the water co-desorption over here. And the moment that I have a 1 to 10 mixture, all of them are 100% entrapped, and they come off exclusively at the volcano, which is indicated by the narrow peak. I also wanted to make sure this was actually true in volcano desorption, so I looked at when water comes off as well. And it comes off when water first recrystallizes. Some of these ices have multiple recrystallization. So this tells us that this indeed happens when the pore size becomes large the first time and the molecules that want to escape are able to. And then I wanted to prove that not just methyl mercaptan could do this. I ran methyl cyanide, methane, and water entrapment. And I find that the enhancement is not unique to methyl mercaptan. And what's nice and proves that this is actually indeed a champagne effect is that the recrystallization temperature, based on that, you can actually see that the methyl cyanide curve for entrapment of methane actually shifts a little bit. And it's about the same degree of entrapment. So this shows us that it's robust. So this has huge implications, pun intended, for volatile delivery. The increased entrapment is agnostic to functional group, sulfur, oxygen, nitrogen. These corks can plug smaller molecules up to 2 to 5 times more efficiently than just pure water. We know they exist because some of these have been detected. And if we were to think of an ice that has actually been irradiated, you would actually think that the chemical complexity decreases as you go to the inner part of the pebble. So this means that whatever is inside, deep in there, is actually going to be entrapped. And so over the course of a disk lifetime, when you have these chemical complexities surrounding the outer shell of the ice pebble, you could actually basically nearly entrap everything that's well below it. This means that volatiles would be retained at high abundances at the water snow line. This tells us that maybe we're actually forming planets with the volatiles needed and might not need to invoke late volatile delivery. Next, we are looking at destruction cross-sections. I think this messed up the order, I'm sorry. I don't know why that happened. So next is my next chapter, which is the destruction of methyl mercaptan. Can methyl mercaptan survive across disk evolution timescale? So this is our figure that I showed earlier, and we actually want to we want to quantify this photochemistry region. We want to know what is methyl mercaptan's destruction rate relative to methanol. Does this change as a function of temperature, matrix, and concentration? So many different dimensions that you can change around in an ice experiment. And does the destruction of methyl mercaptan lead to larger S-bearing complex organic molecules similar to the destruction of methanol, which is very good at introducing chemical complexity? So the way we quantify destruction cross-section is we irradiate for probably 2 hours at intervals of 10-15 minutes. And you can see that the peak that we use to determine how much of methyl mercaptan is there for methanol decreases as a function of irradiation for fluid. And this is just showing how the feature changes as a function of temperature. And you can describe this by this curve, but all I want to highlight is the 2 parameters that we care about fitting, which is how fast the molecule is destroyed, which is your sigma destruction for the cross section, and this how fast do you reach steady state? And that's just the equilibrium between the formation and potential back reaction. So this is just the fiducial destruction of methyl mercaptan and methanol. And we see that methyl mercaptan is destroyed 2 times faster, but they reach about the same steady state. But we see once we introduce other effects, both of them are responding very differently. So here I show pure methyl mercaptan at different temperatures. And what I want to highlight here is that the difference is happening in the steady state yield. These sigma cross sections are staying pretty similar, but your survival yield is decreasing. However, when we look at methanol, not necessarily its survival yield, it's actually its destruction cross section. So what this is telling us is that in this case, whatever the temperature effect is causing, which we predict is probably mobility, the sulfur-bearing molecules can actually move quicker once you introduce the higher temperatures. And as we know, its size its size actually affects its ability to diffuse. So it makes sense that as you increase the temperature, it's able to move faster and it goes into whatever destruction sink that it wants. Versus methanol, you're actually increasing an activation barrier to reaching the same steady state. And so it's able to reach the steady state that it wants at the pure stage, but just faster. I have many different parameters that I looked at, but I'll just highlight one more, which is the effective matrix and concentration. I did this for CO, CO2, and water ices, which are the main constituents. Here I'm just showing methanol and CO. And what I show is a dilute ice, which is very low in methanol, and an organic rich ice. And so what we see is in organic rich ices, you're actually decreasing the destruction rate. And this bar over here indicates what the pure 14 Kelvin baseline destruction is. For methyl mercaptan and CO, we actually see there's no difference, and it's very similar to its pure state. For CO2, we see a slight increase or decrease in the destruction cross-section for methanol and CO2. But we see a slight dependency for methyl mercaptan and CO2. And what we think is that our CO2 is it's most reactive to our lamp flux. So it makes sense that maybe CO2 is reacting a little bit more here. But still, what to note is that its steady state is kind of similar still to the pure state, to the pure value. And then in methanol water and methyl mercaptan and water, what we see is that hydrogen bonding becomes really important in that it's not allowing methanol to destroy. And so we see this gradient over here where methanol is most effectively destroyed in CO, middle in CO2, and then least destroyed in water. And that's because the hydrogen bonds are too strong for it to actually get destroyed, versus methyl mercaptan is actually destroyed most efficiently in water. So here to kind of highlight all the different dimensions that I've explored, about 40 experiments, I have the overview of steady state and sigma destruction. You have the species over here, the different matrix, and I chose the symbol based on their complexity, and then its concentration, and then you have the temperature as well. So a lot, but I'll piece it together to showcase exactly what's different between the two. So just to orient you, bottom right quadrant, you're destroyed quickly and you have a less survival yield. So you're both efficiently destroyed and less of it is remaining at the end of an experiment. And over here, you're destroyed slowly and you have a higher survival yield. Here are the pure 14 Kelvin experiments that were used to get our standard errors. And for that, those are what the bars represent. So these are our baseline case, and we compare everything to this 14 Kelvin. When we introduce temperature, you actually see here quite neatly the opposite effect that they have. Methyl mercaptan's survival yield decreases, but its destruction is about the same, or destruction cross-section is about the same, versus methanol's survival yield is about the same, but it changes as a function of your destruction cross-section. This is in matrices. We see that methanol is most effectively destroyed in CO matrices, which is actually quite a surprising result because methanol, it's actually contested, is it formed predominantly in the CO-rich ice or the water-rich ice? Because there are different pathways that have been characterized for methanol. And what this showcases us is that over the course of disk lifetimes, if methanol is indeed forming in the CO ice, it's probably being destroyed pretty rapidly. This is the species in CO2. We see that it's about the same in terms of the steady state. And methanol also is destroyed pretty rapidly in CO2. And these are the temperature effects. And this is where methyl mercaptan is affected by temperature, but methanol is not. And this is in the water matrix. We see that methyl mercaptan is destroyed most effectively in water, but its steady state stays the same, versus methanol is pretty preserved in water. And as a function of temperature, this is enhanced for methyl mercaptan, which means that it can diffuse pretty quickly. And lastly, I did want to test one ternary experiment where I see if these are actually affecting each other's destruction rate. And what was interesting is that in the matrix that methyl mercaptan is most destroyed in, it's actually the most preserved in when methanol is present. This suggests that methanol and water actually form a potential new ice sink that's much stronger than we would otherwise expect. And so this is something that we want to pursue in future studies to understand the methanol water reaction. So one thing to also know is if it's destroyed, it has to go into something by conservation of mass. So I just show a representative pure 14 Kelvin experiment because that's the one where you have the most bulk sulfur atoms. And I wanted to know if it's destroyed, where is it actually going into? For methanol, you actually form all these new peats, which are ethanol and dimethyl ether. You form water. So you have a lot of new peats that we can easily characterize. And you also have new ones that are hydrocarbons. But then when we look at methyl mercaptan, the only ones that we can actually identify is hydrocarbon. This one over here could be ethyl mercaptan, which is the ethanol analog. But if I gave the most generous abundant integration, because it overlaps with methyl mercaptan, it still only accounts for about 8 to 15%. So what's interesting is that in all of these cases, I showcase that methyl mercaptan is destroyed pretty effectively across all of these different matrices. But we can't, and all the spectra, I dug through it, I was like, okay, what is it going into? And based on the QMS curves, which I won't show today, we actually think that it's going into these sulfur chains or IR invisible sinks. And this could potentially explain why it's so hard to observe sulfur, because it's effectively across all these dimensions destroyed into something that we can't observe. So this is a little summary. What have we learned? Astrophysically, we think that organosulfurs are not likely to survive across disk timescales. It's probably not the sulfur sink. Infrared invisible sinks via photodestruction lead to unobservable reservoirs. So maybe we should look at sample return. Astrochemically, for the first time, we've actually shown that the size of a molecule has an incredible impact on both its own entrapment as well as other icy molecules. And for chemistry-wise, sulfur and oxygen do not behave similarly under all tested conditions. And sometimes they even behaved exactly opposite to each other. And astrobiologically, we know that organosulfurs are quickly destroyed into these infrared invisible sinks and refractory species. So prebiotic syntheses have to think about how to extract the sulfur from this in order to make their chemistry work. So to summarize, astro observations provided these spatial and thermal compositional constraints, and theoretical models showed that we can reproduce observations with certain assumptions that had to be tested empirically. So observations showed we were able to detect organosulfurs, implying there was some way to efficiently form them on the grain. And then theoretical models asked us, can organosulfurs be a sulfur sink? And does sulfur versus oxygen behave similarly? And then what my experiments have shown us, I've provided these new reaction rate network inputs, binding energies, destruction rates, and entrapment efficiencies that can be put into these new models. And some of them are pretty interesting based on size. And my experiments have provided reference spectra that could be used with, for example, JWST to help understand observations and maybe hunt for these organosulfur sinks, and maybe trying to identify new sulfur-bearing sinks based on slight differences in spectra. I have a lot of acknowledgements, and I know that a picture says a lot more than just words, but briefly I'll show these are my advisors, Jonathan and Karin, my committee, Adam and Daniel, Gary, my laboratory manager, Mahesh Rajapan. He's probably one of the smartest people I know. These experiments would not have happened without him. He's literally helped me so much troubleshooting, and even when there were some scares. I'd especially like to shout out my 699 advisor, Eric Gaidos. It was hard to start grad school remotely, but your expertise and breadth and depth and knowledge has really inspired me. I'd like to shout out professors I TA'd for who showed me that I do love teaching, Roy, Duncan, Jean. I'd like to thank my undergraduate research mentors, Richard Plambeck, Michelle Namaka, Elbe Harcourt, the eDisc Large program, the Oberg Astrochemistry Lab, and the Distant Astrochemistry Group broadly, the Harvard Origins of Life Initiative, specifically Dimitar and John, who have shown me that sulfur is actually quite an interesting element. The IfA and CFA grads, and the IfA and CFA staff. There's too many people to thank, but I've written it down in my acknowledgement. So I have all the names written out on my actual documents. I'd like to really shout out astrobites and astronomers for planet Earth, because a lot of my work has also been how can we use our perspective as astronomers to better advocate for our planet. My elementary school teachers who have deeply influenced me, specifically Miss Liu, who is my chemistry teacher. She's the reason I majored in chemical engineering. My family and friends standing across the globe. I know that my family in India has been awake since 2:30 a.m. to watch this. My piano teacher, who's like my second mom, Mickey and Eugene. My dog Taco, who had been with me from elementary school through grad school. My grandparents, Tata and Pati, and my parents, Papa and Amma, and kita ongala lagi cewek muda. And here are some photos because I want to showcase all the people who I couldn't say their names. So this is Edith. This is the lovely Oberg group. We've had a lot of fun together. I've never been in a group with this many women, so that's been really special. Specifically the Oberg lab. I wouldn't want to spend 12 plus hours in a lab in a basement with anyone else. And also, thank you, Mahesh, for inviting us to your daughter's wedding. It was so special to actually be useful to Karan for once, for helping her wear a sari. My IfA friends, I've missed you all, and I'm really excited that I get to be here to celebrate with you all today. My undergraduate research mentors and CFA mentors. A lot of powerhouse women and who have really helped me throughout my grad school career. A lot of grads and postdocs, especially would like to shout out people who made me have fun in the snow. I've never lived in snow before. And the weekend that I moved to CFA, it was 82 degrees here and minus 30 in Boston. And it was like the largest temperature swing that I've ever experienced. And I was quite scared, but they made me have fun in another solid state ice. I had many people come visit me in the lab, which was really fun. So thank you for everyone who's visited me. And I got to visit some labs at HIMB and also the MIT LIGO, which was fun. More friends. I hosted quite a few parties and it was quite fun. And of course, my water. Even when I went to Cambridge, where I didn't have the Pacific Ocean with me, one of my mentors, Nimesh, took me sailing on the Charles River. And I would actually especially like to shout out my lifeguarding, because I did open water guarding for several years. And actually the safety skills I learned there have helped me in lab when I've undergone some serious explosions and stuff, and how to respond pretty effectively. And so, it helped me both surfing and in the ocean here, but actually in lab as well. My Berkeley friends, it's been quite special to stay in touch with you. Some of them were still astronomers, and a lot of my chemie friends as well. A lot of neighbors. So during lockdown, my community in the Bay Area has quite helped me, and I built quite a special community in Cambridge as well. But I'd especially like to shout out all the people in San Leandro who helped me keep going during lockdown. These are some of my childhood friends who have who never see me as the astronomer or astrochemist, but just remember me as Suchi. And then my family, my piano teacher, Mickey, and her partner, Eugene. And then my parents. So I'll end with that. Thank you so much.
Woohoo, go Suchi!
Thank you very much, everyone. So, floor is open to questions in the room and online. We traditionally start with a student question. Alexa.
Yeah, thanks for the really nice talk, Suchi. So as it says on your slide, sulfur and oxygen do not behave similarly. So how does this change any preconceptions or current literature assumptions, given that the previous thought was that they can behave similarly due to the valence electron field?
Yeah, so it has told us specifically size is impactful, and that's something that computational chemistry has not even understood. And the reason I included this in terms of chemistry as well is because it turns out that sulfur substitution of oxygen is important in a lot of scenarios. For example, in the prebiotic way, where they thought that our genetic code had actually sulfur substituted bases, but actually even in low oxygen environments on Earth right now, bacteria or organisms evolve to have sulfur substituted membranes and stuff. So understanding where and when they can be acting so differently can actually help us understand how it behaves in these extreme conditions and maybe even use it. Oh, and one other thing is that sulfur substituted nucleobases are used in like chemotherapy drugs. So because I ran these computational chemistry calculations, which have like a broad array, size has not been something they've really considered in those models because they're limited in what they can do. So this provides like a ground truth for how can we better assume what's happening, because I ran every single experiment with the oxygen analog, so we can actually say the differences that I'm seeing, all else being equal, were due to the atom. A lot of potential impact.
Okay. Hey, go ahead.
Great talk. In the lab conditions, you show that because of the Champagne or volcano effect, we get this really tight temperature dependence for that transition. In a disk environment, is there mixing or migration that you would expect to smear that out, or do you expect a really sharp boundary?
That's totally a good question. We were actually recently talking to some modelers to understand what they might think. And they think that if it happens so suddenly, it actually might affect the dust drift and kind of create this loop within the volcano area, which might be more conducive to formation. But I think it's something we should consider, how to include that sharp release of all these molecules all at once and how that affects the dust and gas interactions, because I think it might be helpful in producing planets.
If you're online, you can raise your hand or just open your microphone and speak, or you can type in the Q&A thing at the bottom. So with that, Jonathan McDowell asked, Jonathan, do you wanna
Sure, if you can you hear me?
Yes.
Yeah. Hey, congrats, Sushi. I'll just read out what I wrote here. I'm so ignorant of chemistry. One of the critical things here for the entrapment is the size of this molecule pore. And I just wonder, is that totally independent of ambient conditions like temperature and density? It's just a function of the bond geometry, or can it be different in different situations?
So that's a really good question. We're talking specifically about amorphous ices. So what amorphous water ice can happen like less than 100 Kelvin. So we're actually just considering those types of ices. And the reason why we haven't had precise constraints on its bond geometry and stuff is because we actually don't have like X-ray crystallography that operates at cryogenic temperatures to actually map its structure. So this was like kind of a unique way to maybe make constraints on what the pore could actually be like. So we're talking specifically about amorphous ices. So this will definitely change depending on the different temperatures, but for the purpose of our studies of the kinds of conditions we care about, amorphous was the ice that we cared about.
Okay, thanks.
Thanks for the question. Yeah, go ahead.
Hey, CJ, that was great. I was just thinking, does the orientation of like an entrapped or captain molecule matter? So like, is it just a certain size no matter which way you rotate it kind of thing? Do you have that a level of detail, a sense of that level of detail of this problem?
Yeah, that's super hard to model, like a cluster like that. Like cluster computation takes a while to run and stuff, especially when you add large molecules like this. So definitely I have no idea how to map it in the laboratory, how we would actually do it. We would have to push it to theoretical chemistry, but I don't think we really have good cluster models that we can run right now. But definitely I feel like the size that I gave was the largest possible size, like our sphere to contain the entire part. So definitely some other ones, like maybe orientation matters, but not enough to make any sort of impact in the entrapment rate.
Anyone else? Anyone else online?
I don't know how you can see the chat or something.
I'm watching the chat, not seeing anything. Then I think. No, okay. It's like an auction house. I will say this is the biggest audience I've ever seen for a chemistry talk. And online too. It's super impressive. So, you really have found a way to sell your work. So that's fantastic. So that's all thanks to Suchi again. Mahesh.
Mahesh, did you have a question?
Oh,
Uh,
no, just congratulations.
Oh.
Hello, just want to congratulate Suchi on this, and so it was a very pleasure to work with her. And so I generally manage the surface science, the astrochemistry laboratory, and basically design the experimental setup, train the students, and so Suchi is one of those students who goes beyond, not purely, there are different people who are coming with different backgrounds and work in our laboratory. So, some people generally just does the experiment and interpret the data and go away. But some people shows much more interest beyond the actual, the experimental data. So going deep into how the experiments are being set up, how the instruments work, and also kind of, we had several talks which are more kind of inspiration either way. So it was a pleasure working with Suchi, and I wish her all the best. And thanks a lot, for coming to my daughter's wedding and make it very lively. So that is. So it was very, it is one of the very few situations. So you can understand what kind of person Suchi is, like more than, so we can talk to her anything, and she is kind of a very, very social person I ever knew. And we get a lot of positive energy. She is always when she's in the lab. So I'm very happy to have actually worked with a person like Suchi and get to know her. So all the best, Suchi, and congratulations.
Thank you, Mahesh.
Elizabeth, yes, please go ahead, Elizabeth.
Hi, Suchi. Congratulations. Normally, I have a lot of questions, but I'm just so proud of you and so emotionally overwhelmed. I'm literally at a loss of a question. But that's okay, because I've asked you probably hundreds of questions, if not more, over the past 2 years. So I don't know. I just wanted to say I'm so proud of you. And that was such a beautiful and phenomenal talk. It was one of my favorite thesis talks. I'm so proud of you. Congratulations.
Thanks, Lisa.
Thank you. I think we can all echo that. So yeah, there's two words of appreciation for your social ability and your work and your great talk. So with that, now comes the hard part, the panel discussion. But thank you all for attending. Hang around for 15 minutes or so and celebrate with champagne in the courtyard, although I may not have brought enough. 6 I'm doing. Take them early.